And it's a delight to introduce our first speaker today, Sarah Peluse from Princeton. I've known her for many years, but in any event, without further ado, Sarah Peluse, she's a postdoc at Princeton, and she will be a tenure-track assistant professor at the University of Michigan moving forward, which I'm very delighted to say. Sarah, and she will be giving a lecture entitled Statistical Properties of the Character Table of SN.
Thanks, Ken, and thanks to him and the other organizers for the opportunity to speak. It's an honor to speak at Andrew's birthday conference. I first met him when I was a graduate student coming here to give a talk. And for some reason, probably because he was so prolific and legendary, I thought he must be 90 or 100 years old. And so I was picturing this little old man. And I think I was invited on behalf of him by Chantel. So I thought, oh, he's so old, he can't use a computer. And then I got an email from him, inviting me to go get coffee. I thought, oh, this is so nice. The guy struggled through writing this email because there was something weird about it, like the font or something. and then I got here and it was early spring and there was ice and slush. And I was so worried this little old man was gonna slip and fall because we were gonna meet to get coffee. And I thought, oh, he's such a sweet old man, braving these conditions. And then I went to the coffee shop and I was on the lookout for someone 90 or 100. And then Andrew introduced himself. I was like, oh, wow, he's so young. So happy birthday. You're not that old. So first I'll fix some conventions. So the character table of the symmetric group on n letters. So since the number of irreducible representations is the same as the number of conjugacy classes, it's a square table. And I'll label the rows by the irreducible representation and the columns by the conjugacy class. And there is a one-to-one correspondence between the conjugacy classes of the symmetric group and cycle types. And then there's a one-to-one correspondence between cycle types of permutations on n letters and partitions of n. That is decreasing sequences of positive integers that sum to n. And there's also a natural correspondence between irreducible representations of Sn and partitions of n, and where the row corresponding to the the row corresponding to the partition lambda and the column corresponding to partition mu will put the value of the character corresponding to the irreducible representation corresponding to the partition lambda of n at the conjugacy class corresponding to the partition mu, and we'll label this quantity chi lambda mu. Okay, so I'm going to write down an example of one of these character tables. So I'll write down the character table of S5. So there are 7 partitions of 5. Okay, so here's the column corresponding to the cycle type 1, 1, 1, 1, 1. So this is just the identity permutation. I'll write down all the other partitions. So this is the trivial representation. These are the degrees of all the characters, all the other numbers. Okay, so one thing you might notice is that all of these character values are integers. And this is not true for all groups, right? If you look at the character table of Z10, they're not all going to be integers. And this isn't just a special property of S5, but it's a general fact that all of the character values of symmetric groups are integers. Okay, so then if you're a number theorist, and we have this nice family of arrays of integers, then it's natural to ask what are the statistical properties of these integers as n tends to infinity? What are the statistical properties of this array of character values as n tends to infinity? Okay, and so the most basic question you can ask is how many of these character values are even and how many are odd? So Alex Miller, based on computational evidence, conjectured that as n tends to infinity, the density of odd entries in this character table tends to 0. So almost all of the entries should be even, which I guess, yeah, you might not guess it from looking at just this example. So Alex had computed the character tables of Sn for n up to 78 mod 2. And he saw that the proportion of even values was tending to 1. So that's why I made this conjecture. So there's also, I guess, a bit more evidence for this. So it had been known since the 70s due to work of Mackay that all of the degrees, or almost every degree of irreducible representations of the symmetric group is even. So we at least knew that Miller's conjecture was true in the first column of the character table. So I'd proved this in 2020. So Miller's conjecture is true. So Alex had also computed like the entire character table, like not just mod 2 of Sn for n up to 38. And he looked at it mod some other primes and prime powers. And based on this, he more generally conjectured that basically the same thing is true for any fixed prime. So if you fix any prime p, then as n tends to infinity, the density of entries in the character table of Sn that are not divisible by p also tends to 0. Right? So Sound and I prove this more general conjecture. Actually with a degree of uniformity in the prime p. Okay, so as long as we let n be sufficiently large, so just large enough so that I guess all the logs and logs in our proof are defined. So just larger than some absolute constant. And p be a prime that's at most log n over log n squared. So then the density of entries in the character table not divisible by p is big O of 1 over n to the 1 over 12p. So it's the update since the last I've given this talk. I think people have seen this a few times in the audience. Is that now we can do it for prime powers too. Okay, so we can also do this, prove this for prime powers into primes, but we're still working on writing it up. So what we know now by like the union bound is that if you fix any positive integer, then as n tends to infinity, almost all of the entries in the character table of symmetric group are divisible by that integer. Are there any questions before am I allowed to ask questions before the end? Or ask for questions before the end? Okay. Wait, sorry, what? Oh, so we just like crudely use the union bound like for each. So we're not doing them like together jointly, how many are divisible by like 6. It's just like these are the number of bad ones, and then we sum up like how many bad ones. I don't think we haven't looked at that, but I think they're probably, I think that would be hard with our argument to look at. That's a good question. That's actually the best question. I'm getting to that. Yeah. So people have cared about that like a lot longer, apparently. So I heard about like this conjecture from Percy Diaconis, and apparently Alex like announced his findings at some like MSRI thing with like all of the like world experts in like the representation theory of the symmetric group. And like no one had thought to look at this before, even though there was like all this interest for decades. And let's see how big of tables of the character tables of the symmetric group we can compute. So apparently since the 60s, people had been interested in this zeros question, but like not until like Alex like actually looked into this did maybe anyone care. Oh yeah, so prompted by that. Yeah, so now we know about the divisibility properties of most entries of the character table of the symmetric group. But there are still some natural questions that we seem to not be able to say much about. So Alex also looked at how many of the non-zero entries of the character table symmetric group are positive and how many are negative. And you notice that about like roughly half were positive and half are negative. So a good question is, what proportion of non-zero character values are positive? How many are negative? And also, I guess the more basic question is, yeah, how many of the entries of the character table are actually just zero? I think I was actually told this was first asked by like Schutzenberger in the 60s. I don't know. So how many zeros are there in the character table of Sn? Okay, so well, I think like computationally it's pretty clear like what's happening here, like half should be positive, half should be negative. It's not really clear at all computationally like what we should expect the answer to this question to be. So Alex only computed the character tables for n up to 38. And I think for n equals 38, he observed a proportion of about 0.36 of the entries are zero. And it's actually pretty hard computationally to go further than this. So not just because there are lots of partitions and eventually you won't be able to fit the character table like in your computer or like in the universe, but also because it just takes a long time to compute these character values. Yeah. So, well, from the data, if you just saw the first 38, it would kind of look like it's approaching some asymptote that when I put more significant digits, people say, oh, that's 1 over e. But so kind of not being able to fit the whole character tables like in my computer, I randomly sampled like 1,000 pairs of partitions of 50 and computed the character values. And it seems that this actually should be decreasing like to like by the time you get to S50, it's like 0.2. I would actually guess, if I had to guess, that the proportion of zeros decreases like 1 over log n. This is my guess. And there's actually kind of a trivial lower bound you can get of 1 over log n just by kind of looking at the distribution of the largest part of a random partition. Yeah, so I think this is the most interesting kind of question about the character table as symmetric group, but I really don't know how to approach it. It's at least one. Yeah. Okay, so now I'll say a bit about the proof of this. I'm not going to really say much about this because there's just not time. Okay, so our proof is based on combining 2 key lemmas. Okay, so first lemma says that we let lambda be a partition of n, which is what this symbol means. And no, I don't want lambda, sorry, wrong letter. I want mu to be a partition of n, and nu to be another partition of n that is obtained from the partition mu. Any p parts of the same size, say m, into one part of size p times m. The character values chi lambda mu and chi lambda nu are congruent modulo p for all partitions lambda of n. Okay, so the columns of the character table corresponding to mu and nu are congruent mod p. So this is proved basically just by, if you're familiar with it, looking at Frobenius's character formula and like looking at the polynomials that appear in that for this character value and this character value, just noticing that they're like the same mod p. So for an example of like what this combining parts sort of thing is, say when p is 2, then the character values for partition 6, 2, 1, 1, 1 are congruent to those for 6, 2, 2, 1. Yeah, because I combined these two parts into one part of size 2, modulo 2. So second key lemma says that if we let lambda be a partition of n, and oh, actually, no, I want mu. I want mu to be a partition of n. And to assume that the largest part of mu is at least kind of a little bit larger than the size or the typical size of the largest part of a random partition of n. So let's say 1 over or 1 plus 1 over L times the size of the typical largest part, the density of non-zero entries in the column of the character table corresponding to mu, or maybe I should write that as number of non-zero values, or the density of non-zero values of chi lambda mu, as lambda ranges over all partitions of n, is at most 1 over n to, I think, 1 over 2L. So the typical largest part is around square root of 6 over 2 pi square root of n log n. Okay, so if your partition mu has largest part larger, significantly larger than the size of the typical largest part, then almost all of the values in the column of the character table corresponding to mu will be 0. Okay, so I'm about out of time. So I hope you then believe our theorem, because this combining parts operation could plausibly lead to your partition having quite a large part. So then most of the values in the character table in that column should be 0. So then you would hope to show that for a typical mu, if you do this combining parts operation as much as you can, then the column of your character table corresponding to mu should be congruent to that corresponding to the mu with kind of all the parts combined as much as you can, modulo the prime. And then you'd hope that this corresponding nu kind of should also have a really large part. Then almost everything in that column should be 0. So almost everything in the original column should be divisible by p. Yeah, so I think I'll stop there. Of things not divisible by, I'm not aware of any. I would guess there's probably, I mean, definitely in like the first column. Well, yeah, actually, I don't know. I bet there's some special pairs or families of partitions for which you could write down some like relatively simple formula for like what the character value is. In general, this is like not possible, but for some special families, and then maybe you could get something. But yeah, I'm not aware of like anything more substantial than that. I can't say much. I guess there's these bounds of like Liebeck and Shalev on like that are used for like mixing of random walks that give like good upper bounds for like certain families where maybe the support isn't very large, but yeah, I don't know. It definitely, I don't think you can get a good enough upper bound to like use Sound and I's result to say like, oh, there are like a bunch of zeros, for example. I don't know. Oh yeah, you can just look at the degrees of like the yeah. Like you'll have one of degree like n+1. Yeah, so I've heard of an REU project that is doing this or has done this for, I know they've done it for like signed partition or signed permutation matrices. And that's all I know of so far. But so from our result, you can get something for like the integer character values like for the alternating group. Yeah, but yeah, and you can kind of control how much that happens. And so yeah. Oh, so that's a good question. So it's known, definitely, I think at least, yeah, I think as like, if you fix p and n tends to infinity, then almost all the character values are 0. Yeah. And I guess if you fix n and let p go to infinity, I don't actually know. Yeah. Oh yeah, yeah. Oh yeah. I'm sorry, could you repeat that? So which measure? Okay. So I think it's still true. And actually, well, if you count, if you count like not a square table, but you count like you pick your irreducible representation randomly and then your permutation randomly, then they're almost all zero. It's also true for Plancherel.